them because they want me to figure out how fast they were going, right after the collision. That's the velocity they had sideways, right here. I'm gonna label that Vx. They would like me to tell them what Vx is. Right? I remember that from projectile motion. Do you remember that from projectile motion? In fact, I will draw myself my little projectile motion chart because it works. Vertical, horizontal. I remember that this is R, this is Vx, and this is T. This is delta Y, this is Vy naught, this is Vy, this is A, and this is T. So R is R. Delta Y is capital H. Acceleration is G. Initial Y velocity is 0. All right, and I want Vx. Seems to me that if I can remember back to projectiles, and I can, because even though I'm old, I remember things, R equals Vx times T. So if I want Vx in terms of R, right, Simon? Then Vx is going to be R divided by T. So I need T, right? I think I got enough stuff to figure it out. I'm going to make down positive so that this is positive and this is positive. And I'm going to use delta y equals 1/2 a t squared plus Vy naught times T. And you should try that sometimes. Try saying one thing but writing something else. I'm good at it, and I don't get enough credit for it, especially from you folks. But you should try it. See what you do. If you say one letter while trying to write something else, I bet you sound silly. I make it sound like it just happened. But you could do it. You could be that good. Yes. And you're not that exciting. So, how about that? Or the people who are also taking dual enrollment physics and AP physics at the same time. You're not really, it's not keeping a secret. It's kind of funny though, you're just not going to that class and just doing just taking their test or whatever and just using what we use here in class. Smooth move there, buddy. I'm just happy that the GPA system is changing now, so none of that crap will work. It's kind of fun. You could have memorized this. Didn't we talk about that? Yes. You should have. You don't, but you should have. That will make this go really fast. That'll be R times the root of G over 2H. That's Vx. Yes. All right? Keep going? All right. What is an expression for H, the height of the ramp? I'm pretty sure that this velocity is the velocity after the collision. But there was a velocity that the block had just before the collision. That one is going to lead me to find out what H is, right? You guys following me? No, am I too distracting today? So I know mgh equals 1/2 m v naught squared, right? I was trying to finish for Cammie, but I guess I won't. So when a student in sixth period said it would be nice if I explained my thought process when I do these problems, I kind of thought that's what I was doing. So I will say, I look at the picture first. So when I look at the picture, I want to notice details about the picture that I think are important. But I also want to know what's happening. And so there are details, but there's an overall thing. I'm getting the idea that something was shot upwards, stuck into the box, but hit it so hard that the box went up too. Is that what you see? I mean, without reading a word, pretty sure that's what happened. Now, I will read the words too, and I'll know what they want me to do, but I'm pretty sure I'm going to be looking at a relationship here between how far I pull that dart down and how high the block goes. Does that make sense? I'm also going to recognize that if I don't pull the dart down far enough, I won't actually hit the block, right? That's a feature that I think later on when I ask about the graph, did you figure out how to represent that? Because that's got to be part of your graph, right? There is distances for which the block doesn't change its height. Did you think about that when you were thinking about this? You may not have, but the first whole part of my graph is a flat line that sits at H1. That represents the fact that the block never moved, right? Just sat there the whole time. Do you have that on your graph? I think you should. Do you see why it should be there? And then I reached a D that is big enough where I start hitting the box. Well, and that's where the problem begins. So let's start with reading the question. Given the information displayed in the image and assuming no losses due to friction or air resistance, please derive an equation for H2 as a function of D, where D represents how far the spring is compressed before the dart is released. To make the problem easier, and yes, this sentence is important, to make the problem easier, you may make H1 the distance from the pullback distance of the dart to the hanging block, regardless of how far down the dart is pulled before release. There's a lot of ways for them to say that in a problem, like assume D is small compared to H1. Something like this. And the reason why you want that to be there is because if you pull the dart down further, technically it changes H1, right? The further you pull the dart down, the bigger the distance is between the dart and the block. What that sentence is doing is saying that that's not true. You don't have to worry about that. That's good for us. Otherwise, it makes it harder to solve the problem. So what they're saying is the distance that the dart is pulled down is negligible compared to how high the dart's going to shoot up into the air. That's another way to say the same thing. So, all right. My thought process, the dart is being propelled by the spring. So I have to figure out how to deal with the spring. And then there's a collision between the dart and the block that signals to me, use stuff about collisions. But the block must be moving after that collision or it wouldn't go up afterwards. So I'm assuming that I'm going to have to deal with the fact that the block now has kinetic energy and is going to keep going up until that kinetic energy is converted to potential energy. That seemed like a reasonable plan of attack here. Here's something you guys are doing wrong. You're going in order. There's no reason to go in order, right? Go in the order that best serves you. I'm going to go in a little bit out of order on this. And I'll show you what I'm going to do for that. I'm going to consider that there's an intermediate part of this problem. There's the part here where the dart has hit the box, but it's still at H1, but the box and the dart have a upward velocity that I will call V2, right? This is right after the collision, but before the box has had a chance to start going up. Does that make sense? Because I'm also going to say that there's a part I have to consider that happened before, where the dart has made it to the box. It's moving, but the box isn't, right? This is just before the collision. That's when the dart's going at, we'll say, V1. Does that make sense? Then there's the part where the dart is just released. So the spring is relaxed, and the dart is leaving the spring, and it has some initial velocity that I will say is V0, right? Do you see these things that I'm assembling here and what they mean? Because there's no point in me going on until you have that established. Sure, V1 is how fast the dart is going just before it makes it to the block. I'm thinking because the dart was shot upwards, it's slowing down the whole time. So I know it's not going the same speed that it left the spring. Does that make sense? Now I have choices on how to deal with all of these things. I'm going to employ the choices that I think work best, but they're not the ones you have to use. You can choose your way. Right? There are multiple ways you could do these problems. I think V0 comes from the spring. And since I'm allowed to ignore the fact that the dart went up a little bit and has a little bit of potential energy due to the length of the spring, I can ignore that and say that we just have energy in a spring, 1/2 k x squared, that's going to be equal to the energy in the dart, 1/2 mv0 squared. Right? Any question about where I got that from? The spring launched the dart. Oh, so I'm good? All right. Oh, I shouldn't use x. It says I should use d, so I'm going to change that x for a d. Got to put it in the terms it wants. So that's the spring launching the dart. Now, the dart goes upwards. Right? Do you see that? When the dart makes it to the box, it's above the reference level. I have some choices on how I can handle this. I could choose to consider that there's a downward acceleration the whole time. And I could use first semester kinematics to relate the velocity of the dart just before it hits the block with the velocity of the dart when it was close to the spring. Could do that. Just a motion equation. Or I could use conservation of energy. Use either one of those. I don't know which one is easier or harder. I'm going to choose probably conservation of energy because that's what this unit's about. But I could just as easily say initial velocity is v naught, final velocity is v1, acceleration is g, and delta y is h. Right? That would work too. But I'm going to say that we are mgh1 plus 1/2 mv1 squared just before I hit the box. Right? And that has to equal 1/2 mv0 squared. Right? If I'm just comparing the dart leaving the spring to the dart hitting the box, the energy has to stay the same. Are we all good? Excellent. I'm going to leave that aside for a minute. All right. All of those m's are the mass of the dart, so I probably should, remind myself that that's the dart because it's going to come up. But all of these masses would cancel out if I was just trying to find the velocity. But I'm doing the problem in the order I want to do. Because I'm going to go out of order a little bit. There is this point here where the dart and block have a velocity, and then the dart and block don't have a velocity, right? It continues to go upwards. I'm just going to talk about this part for a minute because it's the same topic so far. That's still conservation of energy or a motion equation, your choice. But it seems to me that after the collision, I've got kinetic energy, 1/2 both masses, v2 squared. And that has to be equal to both masses, g. And this isn't h, by the way. I'm going to write this as delta h. Because this is how much the system goes up from h1 to where it stops. Everybody follow along? I want to be really careful. h2 is measured all the way back down to the ground, so I can't put h2 there. So I'm just going to put h minus h naught, delta h, like we talked about earlier in the year when we did stuff about gravitational potential energy. Basically what I'm doing, because somebody's bound to ask, is I'm resetting the reference level to be here. I'm saying this is h naught for this portion of the problem. All okay? All right. And there's one more thing to deal with, isn't there? Because if you look at all of this, none of these v's can be in my answer. Right? I created these v's, and so they can't be in the answer to the problem because they're not one of the variables that's listed. So I know eventually I have to get rid of all the v's that are here. But I'm noticing that I have a relationship between v0 and v1. I have a relationship between v2 and the total height. But I don't see a relationship between v1 and v2, do you? That's the collision. That's when the dart was moving and the block wasn't, and then the dart and block are both moving. A collision. I better handle that too. Right, Simon? Excellent. Now, to do that part, I'm going to say, all right, well, just the dart was moving. Then afterwards, the dart and the block were moving. Conservation of momentum. All good? You guys have this habit of having to work the problem in order and get your solution and then plug it right in right away. You might find that just laying this out gives you pieces. Now, this is not the answer, but I can assemble the answer from this by doing a bunch of substitution. And I'm gonna do this actually backwards. I'm gonna go from the end portion back to the beginning. Is that all right with you guys? All righty. So go ahead.
Can you explain why V1 and not V0?
I'm sorry, this is V2. What's that?
Why it's mass of the dart times V1 instead of V0?
Because V0 was when the dart was here, right?
Oh, yeah.
It's going to be going slower when it makes it up there. All righty, so let's put all these pieces together then. I'll do that up here. I'm going to start by taking this one and simplifying it. I'm going to cancel the m's out and get 1/2 V2 squared equals G delta H. That all good? Any question about that? Awesome. I'm going to notice I have V2 here. It's not squared, however, but I'm just going to notice that and realize that I could probably do some substitution to get this in terms of V1 if I wanted. So maybe I'll do that next. Is that okay with you guys? All right. So that means 1/2 times, well, I need a V2 over here, so let's get a V2 over here. V2 equals M dart over M dart plus M box. God, that's a lot. How about just big M? And I'll put the stuff in parentheses later. Is that good for you guys? Big M, fine. Times V1. That's just going to be easier to work with than that whole thing in parentheses for a little while. And why clog up my stuff so early? So MD over big M V1 squared equals G delta H. Doing all right? All right, well, cross that off. I'm down to V1, but V1's not what I need to put it in terms of something else. I am going to notice that I've got V1 here. So perhaps I can put this in terms of V1. Is that okay with you guys? So I'm going to notice all the M's cancel there. And I'll write it bigger this time. G H1. I guess I can't write over there. For whatever reason, it thinks that this part of the screen is weird. All right, whatever. All those lines end right there. Whatever, stupid program. GH1 plus 1/2 V1 squared equals 1/2 V0 squared. So V1 squared equals V0 squared minus 2GH1. I'll wait. There's no reason to take the square root of this, is there? Right? Do you see why there's no reason to take the square root of it? I got V1 squared over there. So I'm just going to leave it in terms of V1 squared. So let's see. I'm going to combine all those. 1/2 times MD over M. V1 squared. So those are both squared. And now V1 squared is V0 squared minus 2GH1. There we go. And that equals G delta H. Doing great. Except, can I have V0 in my answer? No. I have a cure for that, though. Right, there's my cure. I know what V0's related to. So V0 squared equals K over M D squared. Good for me. Is it good for you? All righty. I'm going to grab that, put it up there in my big relationship. Where are you? There you are. Can't hide from me. There we go. So, eek, it's going to be messy. Well, that's just the way of things, I guess. So 1/2 times MD over big M V1 squared. So this is squared. Wait a minute, did I lose something? It's way over. Ah, Mr. Shelton. 1/2 there. That's what I get for you said, how do I think? This is how I think sometimes. Usually I do it more methodically, but I was trying to show you can break your problem up into parts. V naught squared was K over MD squared minus 2GH1 equals G delta H. There we go. All right. This is just the mass of the dart. Let's be careful. This is the big M. That's both masses. And yeah, looks like we could probably put some stuff together if we wanted to. Are you ready to put some stuff together? I'm ready. What I mean by that is this looks pretty ugly and we don't have H2. We're supposed to have H2. So let's start by realizing that delta H is H2 minus H1. And I'm just going to go ahead and put some denominator stuff together. Like these two things are in the denominator. They go underneath that. So I'm going to write it like that. So I'll have MD squared times K over MD D squared minus 2GH1 all divided by 2 big M is massive dart plus massive block. And I'll grab the G from right here and also put it over there, and that gives me H2 minus H1. I'm good for this. Yep. Oh, okay. And I will go ahead and just say that this is minus H1 equals H2. I just move the H1 over there. Fine, I'll make it plus. Do your math correctly. That's a good idea. All right. Yeah. Okay. I might distribute the MD. Do you see that? I probably did on the answer sheet. Because if I distribute the MD, it cancels in the first term. You know, but I'm not sure if that's better or worse. It's just a little silly. But anyways, go ahead. What's your question? The first event was the dart acquired energy from the spring. That's the first event. So that happened first. 1. Okay. Then the dart rose into the air and came in contact with the block. The dart slowed down because some of its kinetic energy was converted into potential energy. That's conservation of energy.
Is that the instant that it hits the block?
It's just before.
Right before. So it's still in.
It's the instantaneous moment before the collision. How fast it was going is determined by that.
Then the next one's going to
Then there's a collision. But the equation's there. This is what happened next. Collision. Which is the instantaneous moment before the collision and the instantaneous moment after the collision. Then the block continued to rise into the air because it has some velocity. So I will have the conservation of energy that I used to figure out how high it rose into the air. There were 4 things. Now, I could have written a problem with part A, find out how fast the dart's going after the spring launched it. Part B, find out how fast the the dart's going before it hits the block. Part C, find out how fast the block and dart are moving afterwards. That's probably how AP will do it. But this is homework. Figure your own crap out. Yeah, there should be a square right there. Thanks. Now, just so you all get the full effect here, you're asked to graph H2 versus D, right? Most everything here is a distractor for that. I mean, everything's constant. Under these circumstances, the only thing that's a variable is D, and D squared. Do you see it? Right? But also, there's the possibility that this is 0. That's when the dart doesn't hit the block. Right? That's a condition that's necessary to understand that the block stays at H1 until a condition is met. That condition is when those two things are equal. So for that D, anything less than that, and the block doesn't move. That's why there's a label for where that is. You should figure out where that is. And it's by setting these two things equal to each other and solving it for D. And if you don't understand why that's true, which I don't think you probably do, it's because that would be if there was no velocity when the dart makes it to here. Right? How far would you have to pull the spring down so the dart just reaches the block? Right? It wouldn't be moving at that moment. You can find that right here. And from there, figure out what D is. But the other part of that is knowing that graph's quadratic after that. It's D squared. Right? So that's what your graph should look like. All right, so we're going to do this one again, because now it's 6th period and not 5th period. In 5th period, I did it more like stream of consciousness, because somebody asked me to perform the problems the way I think about them in my head. That might have been one of you guys, I don't remember. So I did it more of a stream of consciousness. But doing it that way made kind of a mess of the paper. So I'm going to do a little bit different in here. I'm going to be a little bit more methodical, all right? I know what the question asks. I assume you guys know what the question asks, right? When I'm looking at this problem, I'm noticing that there are some steps left out. Would you agree? There are things that just didn't connect. One of the things that you might want to do is start making up your own variable names for intermediate portions of a problem, especially this one. Now, we were given a bit of a gift in this problem. And there are parts of this problem that are being left out, but there's a gift that was given in this problem. And the gift they gave us is that I don't have to worry about the change in H1 if I pull the dart down further. You might not have even been thinking about that, but if I pull the dart down further, do you realize H1 changes? You should realize that, because there's no reason I couldn't have built that in. And I did when we had one of the FRQs first semester with the block being dropped onto the spring. The higher we held it, the further the spring compressed. Do you remember that problem? So that your actual total height had to include how much the spring compressed. We're removing that here. Probably what we're saying is that the dart is shot so far up that the small difference in how far you pull the dart down isn't really affecting H1. Does that make sense? It's a negligible amount, and we don't have to worry about that part of the gravitational potential energy difference. You follow it? That's why that's in here. But that is a gift. It makes the problem a little bit easier. It means D and H1 are not related to each other directly, or in any way. But H1 is a height to where the bottom of the block is. You guys see that? So what I'm seeing is that I pull the dart down, the dart has energy because there's a relationship between the dart and the spring. I release the dart, the spring delivers its energy to the dart, launching the dart. The dart rises upwards, hits the block, and then the block and dart together continue to move upwards until gravity stops the whole thing. Right? Is that what you see? And I've given you the before and the after and none of the in between. So, let's talk about the in between, because I think that's necessary, right? So we'll start with the dart, and let's get a kind of a base in here. So we have something that we can use as our baseline, and we'll have our spring and dart right here. I'm going to put that on the left. This is the dart. Right? So right now it's been pressed down a distance d. All good?
Yes.
All right. Then I envision a point where the dart has left the spring, or is just leaving the spring. It's now got velocity. The spring is relaxed. Right? So there's no more energy in the spring, but the dart is just leaving now. Does that make sense? All right. So I envision now, I'm going to call this V naught. This is the launch velocity of the dart at the instant it leaves the spring. Then there is a future case where the dart has risen a distance h. Right? So this is the distance h1 and is still going upwards. So it still has an upwards velocity. This is just before it strikes the block, the instantaneous moment before striking the block. V1 and V naught are not the same, right? Gravity was slowing the dart down the whole time. So I would expect that it's going slower. In fact, I would expect that that's related to H1. The bigger H1 is, the slower it would be, because it's higher up, right? Now, I know it's also related to how much energy the dart has, but again, I'm just trying to put some things in my head. There's also going to be the instantaneous moment after the dart has struck the bottom. And now the dart is stuck in there, but the whole system is going upwards. Correct? All right. I'm going to call this V2 and note that the whole thing is now moving upwards. All good? I think a collision occurred between V1 and V2, and I'm pretty sure V2 is going to be less than V1. All seems reasonable to me, right? Then there will be kind of this final state. Highlighted by the fact that the string has slack in it in the picture, but the whole system comes to rest. So right now we'll say V3 where it's 0, but we have risen up a little extra high, right? So there's this. And I'm going to draw this because I want to have it here, but I want to make it as faint as I possibly can. So this line represents H1 and is where the block is been hung, right? There. But we are above H1 when we make our maximum height, which is H2. There. I've drawn all the sequences in there, and I think I have everything kind of laid out the way I like. Here to here, thinking conservation of energy, right? The spring delivers its energy into the dart. Here to here, I had options. I could use a motion equation. It's a constant acceleration, or I could use a conservation of energy. I could use either one. That's up to you. I know which one I want to use, and you can use whatever one you want. It's your problem. You have to do it. You understand, too, that if this was an AP question, they'd probably ask you how fast is the dart going when it was launched and how fast is it going before it hits the block. The AP question might step you through it. If you've noticed, AP questions do that. They ask for parts of a problem. I just didn't bother. Like, do the whole thing. This is homework. I'm noticing that from here to here, there's a collision that takes place. I'm thinking conservation of momentum. And from here to here, conservation of energy again, or a motion equation. Take your pick, same thing. It's just going upwards until the final velocity is 0. In fact, what I'm going to do is, I'm not going to do the problem right away. What I'm going to do is recognize that those are these steps. Would you agree? All right. You guys tend to do things like in order, and you start building these bigger and bigger things that get more and more cumbersome to travel with you. I'm not going to do that. For example, I'm going to start all the way to the right and say that, well, from here to here, the block has the block and dart together, which I'm using a big M for. I'll write this down here. Big M equals mass of dart plus mass of block. It's a sum, but I don't want to have to keep writing that thing in parentheses. It's a lot to keep track of. So I'm just going to, for right now, use this. Now, my answer can't do this. My answer has to be only the variables that are allowed. But this is my answer. This is just an intermediate step. And this is going to be M. I'm going to have a 1/2 and a V2 squared. That's the kinetic energy that it has. And I'm going to set the green line as H naught for this portion of the problem. Well, there's no reason why I can't. I can choose H naught wherever I want. And I'm going to say that this is equal to mg delta H. Right? Because the problem actually wants us to find H2, which is this height. But I'm just going to put delta H for right now. It's going to be easier for me to hang on to that for a bit. Makes sense? Now, if you don't want to do it that way, then you have to put a mgh1 over here. Right? And then you can write this as H2 if you're desperate to do so. But you're just going to probably pull this over there anyways and subtract them, and you're going to get H2 minus H1. So for right now, and I'm not doing this to be tricky. You asked me, how do I think about doing things? This is how I think about doing things. Now, I could pop into any other part of the problem I want. I have to do the whole thing anyways. So I could talk about the fact that there's the mass of the dart, V1, before the collision. This is the momentum of the dart just before it hits the block. That has to be equal to the mass of the whole thing times the velocity after the collision. That's just the collision part. Yeah, V1 and V2 can't be my answer, but they can be here now. I'm just doing parts of the problem. You guys okay so far? I'm going to notice that when the dart is launched, it's at the bottom reference level, right? Here. So when I'm looking at that, I think the dart has energy m dart v naught squared down there at the bottom. I know you can use kinematics, but I don't want to use kinematics. I'm going to set this equal to 1/2 mass of dart v1 squared plus mgh1. Right? Conservation of energy. This is how fast, I'm trying to figure out how fast the dart's going right before it hits that block. So I'm kind of working that out too. And then last, the dart got its energy from somewhere, 1/2 k d squared, the energy that's in the spring, which has to be equal to 1/2 mass of dart v naught squared, the launch of the dart. Right? Now, if I was, I don't know, if I weren't good at math, I'd look at that and say, this part, there was no really hard math here, right? The crux of this problem is that I probably want delta H, because that's where H2 is buried, right? H2 is somewhere inside there. That's H2 minus H1. And our problem was to figure out how high does the whole system go at the end. So I need that, and I can't have V2 in my answer. But I look right away, if I try to get V2, I'm going to have V1. If I try to have V1, well, that'll lead to V naught, and V naught will lead here, right? So I could start recognizing that I'm going to have to start eliminating variables here. Do you see that? Now, you guys tend to do this different. You tend to say, start at the beginning and solve for V naught, and then plug that into the next one, getting a more and more cumbersome relationship, which is what we're going to do too. But what I do want to point out is you can choose to do the order that you like. For example, I'm going to notice that in this particular intermediate step, all of these m's cancel out, right? In just that step, I don't have to carry that through. I'm also going to notice, little things like there's v squared here and v squared here. There's no reason to solve for v. Solve for v squared, right? You're just going to put a radical to take the radical off later. So look for things that you can do that might help Or like this. I'm going to point out that I don't have to do any of that if I don't want to. I could just put all of this right here if I want. Right? There are lots of options on how you decide to do that. One reason I didn't use motion equations is because I knew I'm doing the whole thing in terms of energy. Some of the energies might cancel out. Like the entire term be replaced with something else. You see what I'm saying? But you can do this however you want at this point. So I don't have a particularly attached choice. So I think probably, since I have to get an expression, I basically want to get delta H at the end. I could write 1/2 k d squared equals 1/2 m1 v1 squared plus m g h1. Now these m's are the md, right? Mass of dart. There. So I am taking these two things and combining them. That okay with you guys? Excellent. I'm going to do these two next. Combine them. If you don't mind. I'm going to eliminate V2 between them. Because I notice I have V1 here, and I have V1 here. So I'm going to eliminate V2 on the other side there, because I think it'll be pretty easy to do. V2, I don't know where you want me to write this, but V2 is equal to mass of dart over big mass V1, right? We tend to see that a lot in these collision things. A ratio of the masses and the velocities are left over. So, here we go. 1/2 big M times MD over big M V1 squared equals mg delta H. All good? Now, my physics brain is seeing something. Don't know if your brains are seeing it, but I see a 1/2 massive dart V1 squared. And I see a 1/2 massive dart V1 squared. You see what I see? I see a whole freaking term. Might be easier to do it that way. So I'm thinking, let's rearrange this term a little bit. Let's bring that m squared out and get big M on the bottom, right? Because this will be an m divided by m squared. You seeing that okay? Just looking at the math. Pull that one out. I'm going to have an md squared. I'm just going to pull one of the md's out and leave one of them in the parentheses. I'm going to put the 1/2 inside those parentheses with the md that was left over and the v1 squared. You don't have to do it this way. I'm just noticing stuff. Are you noticing stuff? Anybody have a problem with what I just did?
Why did you repeat the 1/2?
Well, I didn't. I just put it inside there. I wasn't repeating. I was saying I was going to stuff it inside there. We all okay? Because now I can just solve for 1/2 md v1 squared and get 1/2 k d squared minus md gh1. Right? Just now you don't have to. You could have solved it for v1 and plugged it in. I don't care how you do it. Just showing you there's other ways to do things. You asked how I do things. Well, this is how I do things. So I would do this going downward on paper. I would not be going upwards. And I wouldn't write it like some kind of bad fever dream all over the place. If I'm doing my homework, I tend to be methodical. But you asked different ways we could do stuff, and I tried to lay it out. Now I'm just trying to eliminate terms, so I'm in the right terms at the end. So I'm going to do my substitution here. MD over big M times 1/2 k d squared minus MD gh1 equals big M g delta H. Great. Let's clean it up. I can't have big M here, so I'm going to clean it up now. We all okay with that? I don't know how you guys clean it up, but I tend to like to make, if I can, something that makes a little bit more sense to me. So I have choices on what I could do here. I am going to say if I divide by the big M, if I divide by the big M on both sides, I'm going to have a big M squared there. And if I divide by the G on both sides, I'm going to have a G down there too. Right? So once I've done that, I could distribute the MD that's on top if I feel like it. But I don't know if there's any, or I could factor out the MD that's in all the terms there. It doesn't make any difference what you do next. You can decide how you want it to look. I'm just going to leave it just like it is. I am going to do this, though. I'm going to rewrite it a little bit. Because I can't have big M in my answer. Now, I should, and you should too, actually isolate H2. There we go, that's our answer. There is something interesting here. You probably don't know to see it because you're blinded by all the things around, but this is a way to do it. It was not sequential. We laid out the whole problem. We created placeholders so we could do the easy stuff, like the conservation of energy rules and stuff like that. Then all of this, everything you see on this screen by itself was just algebra. That's it. Physics ended basically there, right? When we just had each of the sections and we did each of the rules. From that moment forward, it was nothing but algebra. Not fancy calculus, not trig, algebra. Well, maybe algebra 2, but they just break it up. Just because they call it 2 doesn't mean it's anything more than just algebra. Now, I will say this, though. There's a lot of distraction here. So let's get the distraction out of the way for just a minute and consider the things that I think are interesting here. There. The things that control the dart. Obviously, if I increase how far I pull the dart down, I will increase H2. Right? You can see right where it is. If that number gets bigger, the other side gets bigger. Do you see it? I would expect that. I am noticing that if I make the block heavier, it doesn't go as high. Duh. That makes perfect sense, right? Make the block heavier, the dart's going to have less chance of moving it. That's why the only place that the mass of the block shows up is in that denominator. Kind of funny, though. Make the dart bigger. It also doesn't go as high, right? Not only is it in the denominator, but I subtract it on the top. It makes the top smaller if MD gets bigger. You do realize, though, there's also a possibility that H2 is 0. Doesn't that strike you as weird? No, I'm sorry, not 0. That H2 could equal H1. Right, because this term could be 0. That's when the dart doesn't make it to the block. If you look, that's what this ends up saying. This is what happens if you set V1 equal to 0 from earlier. Remember from earlier we had 1/2 k d squared equals 1/2 m V1 squared plus m g H1. That's earlier in your work, or should be. That is the first 2 steps. Energy of the dart, energy of the dart just before it hits the block. Do you remember that? If the dart just makes it there, then it doesn't attach itself to the block, right? And the block doesn't go anywhere. This is why your graph has features, and one of those features needs to be that for a bunch of D's, the answer is just H1, because the dart never made it there. Do you understand what I'm saying? But also, after that point, it's quadratic. D squared.